Welcome to the Digital Architectonics Primer. This is an extensive discussion on how to work with AI on floor plans. Some 4 weeks ago we found a good collection of about 6,000 floor plans, and this was a good set to start and set up a system for this tutorial. So let's have a look how this works. It's available in the cloud. It's not running properly in the cloud yet, but therefore you have to load it for your desktop. You need to put the notebook there. So, sorry for these not working links. I'll have to repair it. So first, what is floor plan graphics about? And there are established ways how to work on texts or sounds on the one hand, which are sequences of data passing by in time, and images or which are partitioning and organizing pixels in space. So, and we'd seen huge progress in the development of neural networks in the last 3 to 5 years, and the principles winning setup for networks in time is recurrent neural networks, and convolutional networks are working on in space on images. This is, for example, language translation or speech to text, and convolutional networks are on image recognition. They are used for autonomous car driving and so on. So there is an extensive discussion in our tutorial Neural Networks for Architects to describe the technology in depth for your architectural background as a beginner. So what is very important with AI, we don't want, different from all the rhetorics in the community, we don't want to talk for classification and prediction, because these are 19th century set theory concepts, and with AI you have another mindset, and therefore I think classification is about making distinctions, and prediction is about making contracts. So you are in a different setup. That, as well as neural networks for architects, in discussion. So in graphics there is no established way how to do that. You can't find good applications for architects in research. There is a lot of with GAN networks. There's a lot of work which is kind of fascinating on treating floor plans like images. So I think this might work with facades, but with the floor plans, I think it's a no-go. It's a conceptual and categorical mismatch. But this is prominent and it works pretty well, but I think it's simply not architecture. It leads in the wrong direction. So let's discuss what the data types are, and then discuss what is different in graphics towards text and images towards topology and geometry, because it's a combination of both. And then develop how to think about floor plans or architectural drawings, making them available to AI, or making an internet of floor plans or architectural artifacts. So All this is more about putting your fantasy into a certain direction than solving a problem and giving you clear advice. This is the way how it works. And there is no established way. Nobody knows how it works. So, but this is the setup. Coding an image is, this is how it works. So you have let's make it a little bigger. So you have a net encoder. This is how Mathematica is doing that. Image, grayscale, you put any image to a 6x6 grayscale data array. So for example, take this image here and encode it. And then you get an array of 6x6. So, and if you want to see that image of code in space, first image, then you get this 6x6. You can do it with 32. Then we will see here, and then you see whatever picture you put in, you always get a vector of the same size. And this is how to work with convolutional neural networks. You need this vector representing whatever you see. So with text, it's different. It's called tokens for the words. You can work on characters, or you can work on tokens. You can work on sentences. But in this case here, you say an encoder with tokens, and the code for time, you encode the words biggest, blah, blah, and so on. And then you get numbers for the words here. So there's a dictionary, and you get indexes to this. And then you have a sequence of just these numbers, and that's the vector of the numbers of a text. And that's enough to do text analysis, classification, sentiment analysis, text translation, and so on. You simply have sequences of numbers in different languages, and if you have one language, sequence of numbers, and then you put another sequence of numbers of another, and you make a cross connection, and then you can do translation. So it's working on these numbers. So in graphics, it's a combination of both. It's important to realize what we are doing in architecture. We're putting space. This, for example, are coordinates, or three-dimensional coordinates, 5 points. This corresponds to the image. And we have time, and then we say, we make sentences like these. These are sentences. We say 1.1 goes to 0.2, goes to 0.5, and this is an area. 2, 3, 5. This is in time. This is a topology. And the graphics is, we have to evaluate that. We have to evaluate that. And the graphics is just rendering this. So this is geometry and topology. So for example, if we go here and say this should be 1.5, we can keep the topology, change the geometry, and then this is what we call parametric design. So in graphics, it's very important that these things are combined and in proportion. Space and time. Geometry and topology. This is graphics. So there's no established way in the research community how to work on this data format of graphics. I don't know. So that's what we want to look at, and we want to make experiments with. So our data set, you can download it here as a zip file, put it to your local folder, And with me it's desktop, it's here, desktop MTP floor plans. Here you can save it, and you can download it, put it somewhere, unzip it. Then you make this here, for example, you start and say, okay, it's on my desktop, it's here, choose, then you get this address, put this address, and for future use, just put it here, so you don't need this dialog. You simply say, to start, say this. Within this directory, there is the code, 4 megabytes, and the indexes of the self-organizing map, the AI, towards the code. So the code is just loaded by this. You see it's code text with this directory given here or here. So this is a data set to load, to work with. Now we have a look at, so each floor plan, we have it here, for example here, high quality, so these are floor plans, and they look like this is data. So we have a scan of the floor plan, and they look very different in different colors, and so these always have to be scaled. In this case, it's 1 pixel per centimeter. It's good, curated in a good way. Then what is done is an SVG. This is we will look at this. This is an internet graphics format, and this is what somebody did 6,000 times. So this is the SVG, and this is the data we will discuss and we will use with our AI, and I have curated this drawing here to prepare this tutorial. So let's have a look how this data format looks like. We can import one of these floor plans and see the SVG. Let's make it in a new, how it is done. It's an XML. Therefore we can use XML. Show all, and here you see it's a light of awful. So we can, for example, find space. Here, for example, space undefined. This is a graphics element here. This is a universal serial number, space undefined. And then you see here, for example, polygon points and so on. Polygon, whatever, style, information, all this. Opacity, stroke, and so on. So this is one graphical element, and this is an undefined space. So, but it's XML, and you can parse it like you parse everything in the internet. So this is how I'm doing it. Give you an idea. Is here. So we loaded the SVG. Let's have a look. So this, for example, the rooms. These, for example, are the rooms. We had the XML. This is SVG. This is what we imported. It's given here, and we have to put it here, SVG here, and then it's assigned to the internal symbol XML, so therefore I'm changing it here. So what it is doing, we're using cases. This is a very important tool. So it's, you say, I want to have all the cases within whatever there is. This can be the whole internet. In this case, it's just the SVG XML of a floor plan. We can have all the floor plans if we want. no problem. Just put in here another symbol or another URL. So, and then we say this is a key. Of cases, the second element is a key, and we are looking for an XML element called G. We saw it, and then we say with the attributes there should be anything before, anything or nothing before or after, but we are interested in class with the name symbolized by A, and the A should be, this is the convention obviously within this data set, that all the rooms by name start with space blank, like we had space undefined. So therefore, if we have a class with space blah blah blah, then this key matches, and then we take all these elements here with B as content. So this is the name, this is the attributes, this is the content. And then we say we want to have a list. This is what we want to do with it. We want to have a list. We delete the space, so we simply have unnamed. This will be here, and then we want to have the first of B, because this is always a list. The first, these are, so if we do this, we get all the rooms. This is our undefined room we had, and we want to just get, because the first here is always a polygons. So then we have, for example, here the lobby, a living room. So we can get more information, but this is what we want to have. We want to have it on all levels. And here, for example, we say I simply want to have the first three. So this is how the key works. And then we just take the result and let's make it with all. This result, and we want to put that into another format. Again, then we take the rooms. So in this, now it's this set of data. We take the rooms, then we look for this this key. So we have always the name. That's it, name, class. And then we always have an XML with polygon points. So we take this as a key, and we are interested in the list of points. Name that A. And then we say we want to do that as an association list. So it's a list of elements where the elements are named. And the name class is CL. Centroid is the centroid of the line of this. So yeah, we do all the polygons within A, so there might be translate polygons is another one. So centroid, points, areas, bounding box. So we make some calculations with these set of numbers. So there's a kind of correction here, delete duplicate. So these numbers are not very nice. So there's a lot of errors in it. So if we do that, then we get a proper list of elements, associations describing what we have. We say it's a class undefined. Centroid is a certain point. The points are here with lists X and Y. So you see, for example, here X and Y is not separated. They're just X, Y, X, Y. We put them into, then we have a bounding box around these points to make life simpler for future, the area for future work. So this is how it works. Put that, symbolize that with a function, put that, and then we directly get the rooms of a certain SVG. So this is how to parse it. So how to render that. It's like this. If we have the rooms like this, we can ask, for example, for the room 1, 2, 3. This would be 1, 2, 3 until here. These are the first 3. So, and then we say we want, from all these, we want to have the the values of the key points. So, which means we just interested in the points. 1, 2, 3. So, these are the lists of points. This is how to access our data set called rooms. To render that, we simply say this should be a polygon, this should be a polygon, this should be a polygon. So therefore we say room, all, not only 1, 2, 3, all points should, each of this list should be mapped to polygon, and we want to have a graphics of that. And then we see this is the graphics. So we have certain challenges here. You see with this slide, so these are different rooms. Then the walls are excluded. Then there are rooms around corners. There are these yeah, it's very fuzzy. And this is not, if you don't have millions of that, then all these minor errors it's a kind of white noise. So this will not, this is not helping. So we need an abstraction from that. And this is what I suggest. So I put this floor plan, the same floor plan, into a function, parsing the SVG, getting the code of this this building, this floor, and it sits here, and make an abstraction of that. So what we do is we straighten all these things. That's the first thing, to make it proper. We distinguish rooms independent of the elements of the walls, just the rooms, and the walls is just another problem. And we put the entrance, this is here, the entrance to the lower left corner. So we always go lower left corner into the building. And we have this x direction, the long direction, and the short direction in y. So to normalize our floor plans. This is what I suggest as a proper abstraction, what we can learn from this floor plan. So it's not about these tiny details. They are white noise, so it's not working. So, therefore, the data format is like this. We strictly have to separate, to make a distinction between space and time, geometry, topology, and this is missing. If you're looking at the, you see it here. So they're just points, and they're somewhere. They're even not towards zero. So that's not working. So therefore, if you want to work, so we said graphics is a combination of both, and we have to keep that separate. Then we have graphs working on topology. So for example, this is a graph. 1 goes to 2, 1 goes to 3, 6 to 7, 8 to 2. If we want to see that, assign it to graph, then it looks like this. So it has no geometry, it makes just a proper stable network towards some, you can have any other shape of it. So, and now we can calculate on the topology. So this is important what we can do there. For example, say which room is neighbor to which room, which window which are the windows of the rooms, the doors of the rooms, and then you have one room via another door to another room, and then your rooms can be connected. All these kind of things are topological things. And this is what you can do with graphs. And here, for example, I can say, what is the shortest way from 3 to 6? And then you use this way. If you go from 5 to 6, then he knows, just go here, straight. Or we can ask for all the cycles. So we can, with exactly the length of 3, so for example 1, 4, 5, 1, 4, 5 is a cycle. And these are all the cycles. It's important as well. For example, in urban design with the layout of infrastructure, streets, and so on. Or you can say, what are the important places? And then, of course, you see one is much more important than the others, and the others are of the same importance because it's all symmetric. This is important. And this is called Pagerank. In this case, we use Pagerank to calculate centrality. And for example, the navigation in internet is supported and weighted by this algorithm, which simply says nodes are important if they are neighbor to important nodes. And this is, I think, very directly pushing our behavior in the internet with social media or with ranking in citation indexes and so on. It's just this algorithm, and we, in our behavior, we adapt to this ubiquitous algorithm in internet. That's it. All this is working on graphs, on topologies. To work with Mathematica on geometry, it's a different set and a complete different view towards, so this is a spatial view, this is the view in time, this is a view in space. For example, we say this is a disk, there's 2, it's a region, and then we can have a Boolean operation, XOR on 2 disks, and then we see or then we have joined. Yeah. Yeah. Okay, you understand that. So just another setup. Or we can calculate the area, or we can, this is not important. So look it up. Like always, go here and go for the documentation to see more on this. All this is a kind of encyclopedia of what you can do with mathematics and symbolic computation. All the cases, so just as indexes. In graphics, it's just a combination of this. This is how graphic format we had it already. Geometry, this is with the regions. And this is the topology. This is how to walk around. This is in time. And this is the graphics for that. This is what graphics is. So we really have, in our data format, we have to make a distinction between these two. So if you go, for example, with these prominent GANs on floor plans to fill a perimeter with appropriate rooms, then you work only on a space because it's working with convolutions and images. So it's just here. So there's no walking around. There's no notion of topology of things. And by that, it's just half the story of what we need as architect. So you don't have time. So what we also need is this, give you an index for this. For example, here we have a rectangle and points. And then we say we want to have a blue rectangle of this graphics 2D. And then we have a geometric transformation. This is my shortcut for it. Geometric transformation. We say opacity red, and then the same graphics. So that's the same graphics, but we need a translation transformation, so we move it 1.1, and before that we rotate it by 15. So we simply take the graphics, make it red, make it opaque, then rotate it. It's a rotation transformation. There's a dot product with the translation, so we rotate it and then move it here to get this result. The same in 3D, exactly the same. Cuboid, opacity, geometric transformation. This is the object. First translated. Now it needs three dimension, a Z dimension. Then rotated by 15 degrees. Again, dot product. If you do this, now we need the graphics. We have this. If you go with 30 degrees, then it's, if you go here for 1.5, then it's here. You can move it up, and then we are here. Yeah, or you can, yeah, whatever. Look it up if you want to. So this is here, geometric transformation. This was too long, therefore I made it. We symbolized that this here with geometric transformation. This is no, rotation transformation, and you can look it up here in documentation. So these are the elements of how we want to, how graphics is done, and how we want to get a data format for this, still with a data format for the floor plans, which can be operated on. You can't just take them as they are. So the code we loaded above, for example here, floor plan number 100, building number 100, floor plan 1, it's this. So you see, this is our data format. We have again an association, key, value, and now this is our geometry, because 98% of these floor plans of our set is orthogonal. I put the geometry just with axis in X, axis in Y to make a grid. So, and then this grid makes points, geometrical points. This is our geometry. These are our rooms, 0.7, 35, 34, 6, 7, and so on. These are our rooms. And then within a room, the segment of from 34.5 to 34, this is 1.66 m a wall and 1.16 m a door by counting the color of pixels. And this is an arrow. This is fuzzy, an opening of 1 centimeter. So we always have, so I'm not really sure how to work with it in depth, therefore I took these numbers and kept, stay with the numbers. So for example, this is a wall, then this is a wall opening a window. So this is a wall and a window in there. So they have all the segments. For example, this room has this segment on the one side. There's another, should be another room. So this is with 35, 34. If it's not, it looks like it's a facade. This is a facade element, because, yeah, you can see it. Good. Yes. And that's important to get the original size. For example, we said we want to flip it or rotate it so that the entrance is on lower left corner. This needs a translation functions or the translation metrics to bring it into the original size. That's it. Our data format. So our code has it for all the 6,000. So take for 300. It's not 6,000. So it's 4,800 something buildings, and a lot of them have 2 or 3 floors. Good. I think you get an idea how this works. So this is all the data you need for a floor plan. Very compact. So this is what we want to take instead of this huge SVG. So we keep it in our data set. We even keep the image on the scan of the floor plan, but we will work with this proper setup. Very compact. So if we want, now we can do certain things with it. This is this is 4,000. We go to 100 again. Then it's assigned to CD. This is the abstract thing. So just this function. In the code, it's down here. You can see how I did it, how to render graphics from this code, but we discussed it a little. So then we have, for example, I made it that we have this tooltip there. You see, if you go over, you see that, which means I can take this thing and take that as a symbol to run, for example, ask, what is it? So I take this graphic as a symbol because I can parse the code of this thing. So again, for example, ask this. This is an interesting thing. It just carries his code. And because of that, I can operate on that, on the graphics, and take that as a data structure. That's very convenient and very unique in Mathematica. Very comfortable. So now we can do other things. For example, take a detailed plan, and then we have a detailed plan. We see all the access, we see the facade, the rooms, the walls, doors, windows with certain symbolizations. Again, you can look up the code and change it if you want to have different. This, for example, is the source. Okay, I have to check it, not working. Now go to 3D graphics. This is how to do these things. I think this is interesting because we don't have to change our data set. It's just another rendering because you don't have to decide anything but assign a height. So let's have a look at this had been our data set, and now we want to do a 3-dimensional abstract graphic of this thing. So let's get all the data. The coordinates are run with these with the tuples. So we city was an association. We want to have the value of this key. These are the axes. Tuples just making pairs of all the pairs, all combinations. And by that we get a grid of points of coordinates. And they are this is the geometry of our building. So then the faces are here. These are our rooms, 7, 35, 34, 6, 7. This is here. 7, bam, 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 bam. So these are our rooms. Then we have the segments n normalized, and these segments are these are the segments, point 34, 35, 34. And now we go replace. This is our source. This is our key, so it will match with this. Not to match with this here, we say we want to only match on level 1, which would be this level. And this is another list here. This would be level 2, so we can match. So, and then if you have A, B, so which would be 8, this is B. So we simply say coordinates of A, this is working like this, coordinates of 1, this is the first coordinate, and then because we can have multiple, 34, 35, if we put that in brackets, then we get 2, we can go 1, no problem to get other things. So we simply say this should be replaced by the coordinates of it, which means our segments here, now they are with coordinates, and then we have the attributes. Good. This is to get the boundaries. Very simple. We have geometric computation. We have all these rooms, and then we directly can say the boundary match is this. So we mesh region goes with the coordinates, and then he says the faces, these are our rooms, and then this is just making it nice looking. So you see, it's just the coordinates, and then the geometry, the topology as rendered as polygons, and then there is this boundary mesh, and then we get this mesh, it just, and then highlight it, this is just the boundary to get a facade. Super simple way, geometric computation. So with regions, as discussed before. So then we say, give us the polygon of this boundary mesh, and this should be our floor. Then we have a polygon. So now with the segments, we would want to say segments, and then we want to have cases. Replace, so this is the first thing. Segments again, so, and we can have multiple replacements. It's a list of replacements. This is the first replacement. This is a key. No, this is the first replacement here. This is a key. So we have the segments with coordinates. So these are coordinates, not indexes. These are the coordinates. Let's go here for segments. So these are the segments, so P1, P2 would be here. We match on level, all levels, so we have this, and then, no, the key is this. We need these round brackets, because this here is competing with this and needs a high, this needs a higher, like plus and multiplication. So you have to make it like in arithmetics. And that is to get hierarchies of and sequence of operations. So in this case, this should be our key. And then we ask if there is a door with number of n greater than 30 centimeters, then make a red line and then put the opening in the center of P1, P2. So this is a little calculation. You learned at school how this works. So do the same with windows, but a blue line. And if there's a wall, then make a gray line without opening. So it's just going from P1 to P2 with a wall. So if there is an element here, so this is important. If there is an element here with with a door, then this is taken and this segment is out. You can't match anymore. If there is window, it's out. Therefore, with the wall, walls with windows or walls with doors, they can't match. They don't match. The same with doors and windows, they don't match. So it's taking it away. Good. Having this, then this is just a translation of this code to a graphic code. So it's a graphic a representation of that. So you don't need anything else. So if we want to render that now, we have in light gray floor 2, and then we have our walls, and then we get the walls, doors, the windows. So if we have that, 3D is the same procedure. In principle we can do this thing here, but it's even simpler because we only need to have these two-dimensional code. We need to take the code of this, so of this, and then we have these two-dimensional numbers, so or these lines. We simply want to have the lines, yeah. So we match on these lines. It's here. It's a case. This is a source. This is a key. X1, Y1, X2, Y2, and then make a polygon with a third dimension, x1 of 0, x1, y1 on h, go up, go to the second point, go down on the second point, and polygon is closing this. So then do that on all levels. So then all the two-dimensional coordinates got three-dimensional, and we always make these loops. The floor 2D just takes the two-dimensional coordinates and make a 0 on the ground floor. If we have this, then we simply can say graphic 3D, wall 3D, floor 3D, neutral and light, and then we have a three-dimensional model. And we still don't need another data model. Yeah? And of course now you can go with depths on the walls and so on. Very few new parameters, as we did with the height. It's just a single parameter to make it 3D. The same with the walls and the facade. Give them certain depth and you are there with 3D. And so, but this is enough. Summary, just the same functions for 2D and 3D, and making it more elaborated, more detailed. So what we can do now is floor plan. These are the symbols I defined. 2D, here, this is the floor plan, abstract graphics 3D. 2D, we can put in a floor plan, and then we get a detailed thing. So the interesting here is it's here, as we discussed before. It's a symbol. You can take these codes as a symbol and then again parse this code to run it as a parameter on this function. So therefore it has got a little complicated here. We want to have the parameters of these things, so we will need that as well. So we don't need it in exactly the same size. So we simply say it's now this is 8 something. We can go. So this is 12 or 13 meters by 850 or something. So now I can put it on 900, put it on 100 and 100 somewhere else. Then in Y it's 900, and then X is 1200. So exactly on that. So if we run this, then it is within this frame 100 and precisely resized to a frame we want to put it in. So because it doesn't really matter whether these things are 5 meter 80 or 6 meter 10, so it's okay. And the important thing is that the doors and the opening, they keep the same size. So we can put it, what this function does as well. So if we go, instead of y 1000 and x 13 meter, we can go in x 10 meter and y 13 meter, and then it automatically turns turns it so that the distortion is minimal. We also can put it into rotation. So for example, we can say this is our rectangle as we used it with the bounding box, and we can rotate it by 45 degrees, so the bounding box is like this, and put this floor plan here. So it's somewhere, and you simply put a floor plan into a rectangle. And you can do it with any floor plan. And of course you want to have the floor plans with very few distortions. So, three-dimensional rendering, the same thing. We have the bounding box in 2D. We have a certain rotation. Bounding box in 2D. Rotation. This always needs rotate to the entry point here. Bounding box. We can rotate it somewhere else. So and then we have a 3D rotated somewhere on this planet. So this simply says rotate and translate it somewhere and scale it somewhere. So therefore the idea of these floor plans of any graphics is that you somehow have a workbench in a normalized way where you kind of construct these things, and then you transport it to any place on the world. So what means is translation and rotation and a little scaling, and it's there. So this is done with this bounding box. Good. Then we can take that as a symbol, get the code. This is working as well as an interesting function. So we assigned this graphics here to GR3D, and now let's go for Blender. And now there's an export. This needs some changes. For example, these 3D graphics is in centimeters as we set it up in Mathematica. In Blender the default is 1 meter, and then X and Y coordinates are changed on these things, and there is a translation transformation. All these geometric transformations, they are not properly supported in this format or this export, so I have to get rid of that. So some modifications. This is I symbolized it with this function. So make this function on any graphics you're doing. Put it somewhere on your computers. So you simply can say system dialog input of file save to get this string as interactively, and that's it. Then you have one obj on desktop, and now we can go for Blender, for example. We have this wavefront, and import the obj desktop, and here we are. So we are still in problem with the rotation. Go here and item, put that to 0 in my default setting, and you see things are as we designed. Good. So that's the whole setup. So there's a bunch of functions. These abstract floor plans can be used as symbols, and we can take any floor plan, put it to any rectangle anywhere on the world, and scale it in a parametric way. So this is the curation of data. So and this is a lot of design. So you really have to know what you're doing. You have to say, I want to go this direction. I want to have this functionality. Then it is working like this. Good. Now we had this sketch of data format for the floor plans. You see, it's super simple. It has conceptually had to be very clear, and I don't think it should be more complicated. So all the details they should be for new AIs in the new levels of details, and these are other intelligences. And you want to be able to control that. You don't want to have an instant solution for things as architect. So for instant solutions, you need millions of floor plans, and then you can have it, and it works. This is not accessible for others than these big global internet players. So therefore we need, we have small sets of data, and then we need stepwise incremental detailing of our plan. And I think it's more adequate for architecture to do it like that. So, and each of these steps needs a proper adjustment of abstraction. So, therefore, another AI for rooms towards furniture, precise positions of doors and windows, and so on. And then you can run it iteratively, a system and a sequence of AIs. I would say this is appropriate. So, now, to establish an AI, we want to have unsupervised learning, and we're using the self-organizing map by Kohonen in the 1980s. And it's working pretty well. This is my favorite algorithm. Here you see the code itself. This sets up the data structure. This is a training. This is the algorithm. It's not more. It's very important to realize. You can address any problem just with this algorithm. And it never is much more complicated. All the algorithms then for the neural networks, the principle is always like this. Very few things, very complex to understand. So it takes years to understand why the hell this is working. So then some supporting functions, and this is the interface to make it simple to use. That's it. Now let's give a short introduction how it works. Close it. So it's always AI. All AI always works with vectors, just with numbers. So you have to translate any kind of event or object or element into a vector, which is characteristic for this event and can be compared with similar events and so on. In this case, now we make an example just with colors. So these are 3 dimensions to represent colors. And we want to work and map these colors and cluster these colors. So here we have 10,000 colors, and they look like this. So we can take the first 12 colors, map them to the RGB color renderer, and then we have these colors, completely random colors. So our interface simply says take all these vectors and make a 12 by 12 map for it, cluster that. So it's a kind of spectrum of what can be experienced with these 10,000 events. And it looks like this. So so now we started, trained, everything is there. And now we can ask any kind of color, for example red. This is red, green, blue, so this is pure red. What do you think about that? And then he says, okay, it's something about, I cluster it into this. So this is a mean value of a lot of different colors. So we have 144, so this is, and 10,000, so it's about 70 colors, and they are clustered in this segment, and their mean value is this. And he interprets and says, this is my unit. I would put it in. If we look at all the units, then it looks like this. And you see what we have is a spectrum of the events. So he understands conceptions like green, red, blue, yellowish, and so on. He understands these kind of conceptions. And he simply says, what if I take, for example, the color red, then this is the color, then it's just the first corner, which is most likely this. I would put it there. So by that you can say, okay, there's a lot of friends around which have similar colors, and you can ask for these friends, and these are the colors of this unit. So, and you can ask it like this in a one step. So these are the colors, and if you want to see these colors, then you see all these reddish things almost the same. So you give no name, you give nothing, you simply say, this is my event, and try to find friends. So you can do it with an infinite, it's just limited with your computer, so with your computer and power, how many dimensions it is for illustration, how it works. It's like this, and it starts. If we initialize the self-organizing map, we have random color here, so it's white noise. And you train it, simply this is the algorithm, you train it by throwing an event into this array, and then it just falls to the pixel, to the unit, which is nearest to the event, to the most red pixel. And then he makes a kind of wave, so it makes a little more red to the environment of his specific color. So and then the green and the blue and the red again and so on, and by that these things, if you do it 100,000 times, these things gets a kind of understanding of what is going on, and maps, gives you a spectrum, a map of all the events around. So we will do the same with floor plans, and the floor plans will only have four dimensions, and we will see it works exactly the same. So let's have a look how to work with floor plans. Here we are. So we load the data set. We did that already. With the code, everything is there. Now we load a pre-trained self-organizing map. So it's it's part of your directory. It's here, this is a file. It's trained. So now, if we go, like we did with red, if we go to a certain unit in this self-organizing map, we get the numbers, the index to the vector of to the vectors. We had 10,000 in with the colors. We have about 6,000 with the floor plans. So these are the different floor plans and the indexes to the floor plans, and they all the same. They're all like reddish or whatever it is. The vector we are choosing is this, so we can look it up. For example, 8 to 22, it's this, and then this says building 668, floor 1, and this is a vector we choose, not RGB. We use axis in X, axis in Y, then meters in X and meters in Y. So the width and the height of floor plan. So this is our vector, and this works surprisingly well. So we have the size, and we have the kind of granularity in X and Y. And by that, because there's always included a certain meaning, because they're all floor plans, we don't have to explicate what it is. It's always good to have very abstract calculations to and numbers characterizing the data itself. So you don't have to represent it. You don't have to think, I have to understand the floor plan. You simply have to say, what is the characteristics of it? The most simple characteristics, which makes it measurable, it makes similarity measurable. So I started with these experiments, first with just counting the rooms, looking for the names of the rooms, looking for the proportions of the rooms or the sizes of the rooms, the numbers of the rooms, and so on. And all this was not very performative. And now with these axes and the sizes, done. Works very well for our purpose. This is to be invented. So, if we have it, for example, here, this was a way how to, now we can go for the code. This is the code, we know. And because we have this code, now we can go for the graphics, the principal graphics of it. So, therefore, now we ask, do the same thing, but we ask, let's go here. And therefore you see it's important that you interface your data, yeah? So, because it's just numbers, and you just have these indexes, you don't have more. And you have to put these indexes back into your context and to the real thing you are interested in, you want to reason about. So, for example, these are the indexes of unit 24. These are the numbers of the floor plans, the indexes to the floor plan of the unit 24. So it's a certain color in this spectral space map. So then we want to get the vectors. So map this, go here, map this here, map it to the vectors of the self-organizing map. Then we just take the first one. So this is building 429, floor 1, and so on. So these are our friends in a certain unit. They found themselves in a certain unit. So put that to these graphics here. Put this to the graphics, and then you see we have it here. You can easily ask for some else, then you get different abstractions. Good, yeah? We have 144, so we have 144, that's the last one, 125, and then here we are. Whatever. So, this is to get the friends. So like with the colors, exactly like the colors. Now we can make this spectrum. So we had this rainbow map with the red and bluish, greenery, and so on. This is the same set for our floor plans. So this is the spectrum of the floor plans. What we did do with this function here, go for all the 144 units, 12 by, in this case, no, it's not 12 by 12, we have, I think, 20 by, we can count it, so this is 12 by 36. So we have 430 units. So 12 by 36. So and it's not only that's important as well, they can contradict. So it's clustering, not only by X and Y. This would not be sufficient. It's clustered by how granular it is, and therefore it's getting a little fuzzy. So it's folded in this multidimensional space. It's folded and it's mapping it to X and Y into these simple clusters. So, and that's interesting. These parameters can contradict. So you don't need precision there. It's just a little fuzzy. So it learns the spectrality of, it's a manifold. So now we can, as we did it before, we can take any kind of these elements and we can ask for the ID, and then we see this is the building, that's the floor. Then we can ask for all his friends in the simple graphics. We can ask for the details, and then we have a detailed plan. And we can ask for 3D graphics. It's 250 height, 128, 250. So then we get a simple graphic in 3D. So we also can ask for the source, just get the reference. So because we want to work with it, we don't want to have it directly there, we want to work with it, and then we can look and learn. This is what we want to do. Good. That's how it works. I hope you get the idea of the spectrum of all the events of the floor planishness. So it's the Internet of Things, and then these things are somehow communities, clusters, and so on. And you want to be able to talk with them, ask questions, and find friends for your new project. So that's how it is. So then it's a question of interface. It's not, now we go towards the application. What we want to have is that we say, we have, for example, a width of 1000, a height of 1000, then we say 4 in X and 6 in Y. It should be organized more like this, instead of like this. And a height, so we want to have maximum 100 elements. So this is the floor plan we suggest. And we ask, give me a floor plan which fits to my vector. So it's the same vector. This is a vector we used to train the SOM, and we have this vector as a characteristic, four-dimensional vector to characterize a certain floor plan. So we just take this to ask the system in a simple way, give me maximum 100 of that. So give me 12, and then you get 12 samples of this, and then you get a random selection of this if there are thousands. So then you simply say, okay, that's interesting, and then you take one. So, or for example, if you change the granularity here, then you get different things. So now you see they are not organized precisely in X and Y. If you go here, they are organized in Y direction. If you go with 6 here, then you are organized differently. So take 6, then we are here, or 4, 6, take 24 maximum, then we are here. So now we have it. We have this selection here as a cell, so we can ask for the first one. This is here. We can ask for the fourth one. Then we have this one, this guy. And now we want to adapt it to a certain frame. So we had and say, because this thing here is, we can look it up. This was the function. So we can look it up here. What is this? And then we can say frame true frame. And then we see what it is. So it's we asked for 1000 by 1000, and here this is 900 something, and here it's a little more than 1000. So what we can do is we can say we want to have the bounding box. So and say this should be height and this should be width. These are our numbers here. Oh, let's go here with this 900. So then we have the first one, and then you see it's 900 here, it's 1200 here. So if we go with the next one, then it's almost, but it's slightly different. Yeah, it's good how it is sorted, but it's not precise. So therefore we can simply say, no, it's precise because here we put it to the bounding box. Now you see, this is the actual size. It's 900 by 1000. And if I put it to my, then it's stretched a little. Good. And now all of them are of the same size. And here we do it just with our selection and make it, can switch it. So imagine you have a parameter and then you ask, what can I do? And then you get all these samples. I think you get the idea, huh? It's not perfect, but it's a sketch to trust thinking about AI and supporting your work in a certain way. So this needs always a lot of computing power in backgrounds, therefore always, if you want to have it back, take it, but delete it. So now if we have this system, now we can play around. So first thing is, again, we have a width and a height. Then we go with 6 by 6. These are examples. And now we, instead of iterating and trying to find a good one to start your design with, this, for example, aggregates them simply on x direction. It aggregates them in a direction. Make them. I'll go here for another one. These are these one, and now he gets them. So they are all of the same size and of the same width, and then put together with a simple function, map index. Now export that to one OBJ. And then go here, and here we are. It's a little unfortunate in my default setup. So, but it's working. And that's interesting. These things are you can't do it by hand, huh? You would be crazy. So you somehow can paint, like with a brush, you can paint these things like coloring. or putting texture to it, and by that it's unfolding. That's a very surprising thing. So this is what I'm always telling you. Architecture is not any longer about drawing and about graphics. So you have to talk, you have to do these proportions on numbers, on certain characteristics, and by that you are modeling a character of your building. And this detailing here in graphics, this is just coming. So even if these floor plans are super stupid, this looks reasonable. Huh? You really have to look. So you can improve that, but it's not stupid at all. So if you make nice stories, it works. And you know that this floor plan, if there's your data set, is of reason. So you don't have to, and it has a reality. You don't have to rethink all this stuff again. So it's like before AI, it's about taking colors to make something vivid. Now you can giving these structures and put them to make a certain gesture, a certain story alive. So let's go on. Take this away with other things. For example, here now we have boxes, so we make a grid of rectangles, and now we render these floor plans into these boxes. So this is the first box, 000 to 600, then 600, 600. So this is the first box here. And the second box is continuing with the length of 800 on top of it. So we have this 600 box, we have this 800 box. So if we do it with all the boxes, then we get a floor plan, and they're all reasonable because they're only distorted a little. So do that with a lot. You have this. Go to export again, and it's here. It's not selected item. It's here. Of course, you can build cities with it easily. Not too bad. Now it's stupid, a kind, but it's interesting in the taste. So and I think you have to find setups which using all this technology not to make stupid things. So make a grid of these things is just stupid. You have to make proper stories about a proper characterization of what you want to have, and then these machines can do that, the detailing. This I think is important to understand. So go further, and then you see it's just playing around with it. So for example, now we take out the center, and then we get a ring of floor plans, and we always get a new one. So we can have, because it's random, selection of the floor plans which fit, and then we get always new ones, and we can put that into it's just this code, we can put that and stack multiple of these floor plans. In this case, these are where are the 12. So take 6, for example, that's too much. Now we have 6 floors, and we stack them. So the idea is that the big ones, 14 by 14 meters, there's an apartment at this edge, And there's a 6 by 6 meter is here on this edge, and this is interpolating. This is 6 by 14, and this is 14 by 6, and then interpolating. Putting that 6 times, done. So each apartment has front and back side, and on the edge they have 2 front sides. You can make staircases, lifts in the inner side. This is the public side. Very simple. Take proper, nice designed floor plans, not these random 6,000 things, stuff, and here or there. It's interesting. And yeah, good. Put that to your renderer, and then you're here. Again. Here we are. Make nice renderings. So it's still stupid, but not too stupid. Yeah, let's see. This is a proper apartment. This is the one. Interesting setup. Intellectually. Now there's a lot of architectural questions around this, and that's the principal setup. I think I'm super fascinated by. So technology is enabling a more abstract view on architecture itself. Good. That's in principle the story. There are, now we have to go links, we're working only in. So what we did in 2007, it was this here, and it's in our book, Beyond the Grid. There's a lot of examples of things you only can do with computers. And here, for example, this is a building block made of some 50 or 60 famous floor plans in Zurich, three floors. And then, of course, we have the staircases at certain point, which makes the adaptation of the floor plan a little more complicated. But in principle, that's it. Then here you have all the different rooms with their qualities, like BIM, instantly there. We can do it with this building as well, what we had. So, and then we had this kind of facade. That's it. We did the same thing in here in Herzogenrath. This is for laying out the plan of a new built village. Yeah, that's it. Slightly different setup for a building, aggregation of rooms for a building. That's one, and the next one is it's interesting at this. This is the first company I found with my brother, and it's here. So, and you see with these buildings here, and this is the infrastructure, and they are organized the same way. So you see all these are repetitions. It can be amorphous, so it's not a problem. So, and the building is organized very, in this case, in a rigid way, but then you go and you simply plug in, like we did with the floor plans. You plug in layouts of technical infrastructure, like a floor plan or like furnitures. for the living room, for the kitchen, and so on. So you have a certain topology, and then you have a room, and then you have a map, an AI, suggesting certain furnitures, or suggesting certain technical infrastructures, or suggesting a floor plan for a perimeter, and so on. And by that, you're super fast in adapting. And these are then the principal floor plans. These are the principal layouts, and you adapt them automatically there, and done. It's and your 90% of the work is done. And in these kind of buildings, this is first you see it's all repetitions, not so problematic, and it's 50-60% of the investment is just the orchestration of that, and which gets very prominent with building information models. And you can reduce the amount of data for building information models with that, as you've seen that with the code we have. So it's near to nothing. You reduce it by 90, 95, 98%. What is there with building information models? And you're super precise in connecting all the things in space with very few code. I think that's it. Thanks for watching, and see you in the next tutorial.